Hello and welcome back to Atomic Math. Today we're going to talk about how we can use matrix to solve linear equations. So first of all, a linear equation represents a straight line. We have things like this: x1 minus 2x2 equals minus 1, or minus x1 plus 3x2 equals 3. Now, a solution for x1 and x2 satisfies both equations if the point lies on both lines. A solution is where the lines would intersect. So this would look like this. So we graph our two lines and we can see that they cross at the point 3, 2, which means x1 equals 3, x2 equals 2 is a solution to that system of equations. Now, we could also have lines that don't cross at all. We could have equations like these two that when we graph them, we can see that they are parallel. They don't cross at all. Or we could have ones where the lines coincide, as in these two equations where one is sort of positive and the negative version of it, and they coincide with each other, meaning they lay on top of each other. So this one has no solution, and this one has infinitely many solutions. So basically, a system of linear equations is going to have three options: either no solution at all, exactly one solution, or infinitely many solutions. And exactly one solution or infinitely many solutions, this is what we would call consistent. And if there's no solution, we would say it is inconsistent. So if we look at this equation here, x1 minus 2x2 plus x3 equals 0. And then we have this equation here, 2x2 minus 8x3 equals 8, and minus 4x1 plus 5x2 plus 9x3 equals minus 9. Now we can use a matrix to solve this system of linear equations. We could simply put the coefficients of each of the variables into a matrix. So we would have the first column representing x1, the second column x2, the third column x3. Now, this is what we would call a coefficient matrix, but we can also have something called an augmented matrix. This is going to include the values on the right of the equal sign, and it's going to look like this. So we have added this extra column, and it's representing these numbers here. So in order to solve the equations, we must use row reduction to get the coefficient matrix into a reduced echelon form. And by that, I mean this piece right here. We need to get into reduced echelon form. So let's take a look at how we can do that. The first thing I would want to do is to get rid of this minus 4 right here. So what I would do is add 4 times row 1 to row 4. So 4 times row 1, I'm going to add that to row 4, and my new value for row 4 is going to be 0 minus 3, 13 minus 9. Now I can add that back in. So now my matrix looks like this. Now I want to make this 2 a 1 by multiplying the row by 1/2. And if I do that, I'm going to end up with this matrix here. So now you can see the first column I have 1, 0, 0. That's what I want. In the second row, I have the 1 in the leading position, but I want that minus 2 and minus 3 to go to 0. So the first thing I'm going to do is I'm going to subtract 3 times row 2 from row 3 to get rid of this minus 3 right here. And if I do that, I'm going to now have this matrix. Okay, let's move this up. Now I want to get rid of this minus 2. And to do that, I'm going to add 2 times row 2 to row 1. And once I do that, I have this matrix. So now you can see both my first column and my second column are in the form that I want. Now I just have to get the last column to have zeros where we have that minus 7 and minus 4. So if we add 7 times row 3 to row 1, we will get this matrix. And if I add 4 times row 3 to row 2, I will get this matrix. So now my matrix is in the form that I need it to be, and I can now read off my solutions. So basically, x1 is going to be 29, x2 is going to be 16, and x3 is going to be 3. So my solution is 29, 16, 3. So we can also go back and check this. We had our original equations here. So if we plug them in to the first equation, we find that it is consistent. If we plug it into the second equation, again, it is consistent. And if we plug it into the third equation, again, it is consistent. So that means that 29, 16, 3 is a solution of this system of linear equations. So that's how you can use a matrix to solve a system of linear equations. If you like this video, go ahead and hit like. And if you want to see more videos like this, hit subscribe. And I'll see you in the next video.